So today we're going to deal with topic 32, graphing exponential functions. Now many of you might be familiar with exponential functions because it was addressed in Algebra 1. So now we're going to use what we've learned so far in Algebra 2 and kind of add to that. So we're going to start with what is an exponential function. So any function in the form a times b to the x power, where a and b are constants, with a not equal to 0 and b greater than 0, and b cannot equal 1. So there are a lot of conditions here. Basically, we have numbers in place for a and b. A cannot equal 0, otherwise our entire function would be 0, and we just get y equals 0. So we just get a horizontal line. B is going to be greater than 0, so we're not dealing with any negative numbers here. And b can also not equal 1, because if we have an exponent, a number raised to an exponent, and that number is originally 1, the entire thing will just be y equals a, or y equals a times 1. So if we look at our first example here, we have graph the function f of x equals 2 to the x. So if we think about what our a is, now we don't have any number specifically in the a spot here, so that means we're really multiplying a 1 times this. So a here is 1. Our b is whatever constant is raised to the exponent, so our b here is 2. Now our a is called the y-intercept. So whatever number we have here, when we plug in 0 for our x, that entire b to the x will just reduce to 1. So we're left with our a value, also known as our y-intercept. Our b is called our multiplier. That's kind of our constant that's going to continue throughout this entire function. So just like we've made tables in the past before for polynomials, for quadratic functions, for linear functions, we're going to make one for our exponential function. So if we plug in -2 in for x, let's get a different color here. If we plug in -2 for x, we'll plug it into our function. So we'll get 2 to the -2. And we know from our properties of exponents, whenever we have an exponent to the negative power, that's the same thing as 1 over 2 to the positive 2 power. So if we bring that exponent down to the denominator, it becomes positive. So now this looks a little bit easier to simplify. We know that 2 squared is 4, so it reduces to 1/4. Same thing if we plug in -1 for x, we get 2 to the negative first. We can reduce that to 1 over 2 to the positive first, which is just 1/2. If we plug in 0 here, we have 2 to the 0, and we know that anything raised to the 0 power is just 1, which shows that this is our y-intercept. And we know that from here that the number in our a spot is our y-intercept, and this just proves it. Now if we plug in 1 for x, we get 2 to the first power, which reduces to just 2. And if we plug in 2 to the second power, that reduces to 4. So here are all our points. Now we're going to plot them on an axis just like we would beforehand. On a graph. We will use our axes. So we can go over 2, up 1/4, over 1, -1 I should say, up 1/2, over 0, up 1, over 1, up 2, over 2, up 4, and this pattern is just going to keep continuing. So it's just going to keep extending there. and that is our first exponential function. Now, if we look at the key features of this, there are 5 key features. Some of them we've addressed beforehand. So something like our domain, which is all of our x values. So if we look back to our function beforehand, our x values, we want to look on our, get a different color. Let's do red. That's everything on our x-axis. So if we were to zoom out on this graph, we're going everywhere from negative infinity to positive infinity. So our domain is going to be negative infinity to positive infinity. And we're going to use parentheses here because these values are not finite. If we look at our range, the smallest y value here, again, we're going to look at our y-axis now. The smallest y-axis here, y value is 0. We don't go below the the x-axis. We don't go below the x-axis. So our smallest y value is going to be 0. And our largest y value is it's going to keep increasing until we get to positive infinity. Now here, we are also going to have parentheses because if we look at our graph right here, it's going to get infinitely closer to 0, but it's never going to actually reach 0. So our range is 0 to positive infinity, but we're going to use parentheses because there isn't a finite point where it stops. Our y-intercept we can take from our table, again, is just at 0, 1. And now we're dealing with asymptote. So the asymptote is the value that the graph approaches, but actually never touches. So this can be a vertical line because we're going to write it in the form of an equation, or it can also be horizontal. So if we look at our graph here, the value that our graph always approaches but never touches is right at our y-axis. And oftentimes, these asymptotes are identified by dashed lines. So this is our asymptote. And this is right at our x-axis. So we can say our x-axis, or if we want to identify it as an equation, which is preferred, this is going to be when y equals 0 because it crosses the y-axis. Now, last but not least is end behavior. So this kind of relates to our domain and range. If we look as x goes to negative infinity, what happens to y? So as x goes to negative infinity, y goes to 0. Remember, it never goes below that x-axis there. And as x goes to positive infinity, y also goes to positive infinity. And we can look there as well. So as x keeps getting bigger and bigger, so does y. It keeps getting bigger up there. We're going to move on to our second problem. So our second problem, if we look at our A value here is a lot clearer. It is 5, and right here, our B, our multiplier, is 1/2. Now notice here how our multiplier is not a whole number. Now that's fine as long as it's not a negative number. And we also know that looking at our A, this is going to be our y-intercept. So same thing as before, we're going to plug this in to our graph, to our function to get our values. So we will get 5 times 1/2 to the negative 2. We'll have 5 times 1/2 to the negative 1. 5 times 1/2 to the 0. 5 times 1/2 to the first, and 5 times 1/2 squared. So these are going to give us all of our values. If we simplify this using our properties of exponents or also on our calculator, we're going to get 20. When we plug in -1 for x, we're going to get +10. When we plug in 0 for x, remember this is where our multiplier reduces to 0, so we just get 5 times 1, or 5. If we plug in 1, we get 2.5, 2.5. And if we plug in 2, we get 1.25. So here we can plot this on our graph. Go over -2, up 20. Now this is definitely going to be off our graph. So we'll say that's +20 up there. We can go over -1, up 10. Please note that this is definitely not to scale. Over 0, up 5. This is our y-intercept. And again, I'm just following along with what's said on the table. Over 1, up 2.5. Over 2, up 1.25. And so on and so forth. Now, if we notice the pattern here, our graph is going to keep following this trend. And there is our exponential function there. So moving on, if we want to look into our domain, if we look at our domain here, our x values, again, are going from -infinity to +infinity. So we're going to have our parentheses. Our range here, again, we're not going below the x-axis, so we're going to have 0 or above, so 0 to +infinity, and it never stops at 0, it just approaches it, so that's why we have our parentheses right there. Our y-intercept is right at 0, 5. Our asymptote is the value that our graph is going to be approaching. Here, if we look at our graph, it is also our x-axis. So this is our asymptote. So our asymptote is also our x-axis. And here that is in an equation form as y = 0, since it crosses the y-axis at 0. And our end behavior, as x goes to -infinity, y goes to +infinity, keeps going up and up and up. So as x goes to -infinity, y goes to +infinity, and as x goes to +infinity, as x keeps getting bigger and bigger, y keeps approaching 0. So y approaches 0. And there you have it. Those are our first two problems with graphing exponential functions.